Hi, my name is Devin Bost, and I'm going to be talking to you today about how to leverage Apache Pulsar, which is an innovative streaming technology. And we're going to be talking about really the business case of how critical real-time data processing is for your business. So, as I mentioned, we're going to be talking about the business case. Good data requires seeing the end from the beginning. For example, you can't build good machine learning applications without good data. Your data has to effectively represent the problem that you're trying to model. And that's more challenging than you might expect at times. Especially in today's world, we have lots of different data sources. We have data variety. This introduces data integration challenges and leads to the need to have good data fusion. We're going to be talking about some of these paradigms and really how they've evolved and why streaming technology is so valuable to be able to solve these problems effectively. So, more than 90% of startups fail, and perhaps it may be surprising that the primary reason is due to self destruction. In the book Nail It and Scale It, the authors talk about how, of 9 out of 10 companies that fail, the reason that those companies failed wasn't because they couldn't build a product or solution or provide some service to their customer. The problem was that they actually missed the mark. They didn't build the right thing. And so why do these companies fail? Well, they they didn't build the right thing because they didn't first deeply understand the problem that they're needing to solve. And so managers, they tend to start by building solutions, but we deeply emphasize the need to first understand this problem inside and out. And so, as an example, let's say you're taking a flight to Honolulu. Let's say you're off by just a tenth of a degree. Well, you're going to end up in the middle of nowhere, out in the ocean, right? And what happens when you've used up all your gas, right? If you used all your resources to get to that distance, and now you're not at your destination, right? Well, that slight error is going to cost you everything, right? And in this case, you would die because you couldn't actually make it to your destination, and the plane is going to crash in the middle of the ocean, and maybe if you're really fortunate, then there's some miraculous way that you could be saved, but there's definitely risk that you're a goner. So organizations enter the state of decline when they fail to anticipate, recognize, avoid, neutralize, or adapt to external or internal pressures that threaten the organization's long-term survival. And what is the greatest pressure on companies today? It's technological adaptation, and it is unavoidable. You can't avoid it because it will catch up to you whether you like it or not. Okay, let's think about the internet, right? Let's think about the companies that decided that they were not going to use the internet. Well, what happened to those companies? They failed. Society has advanced. Now, we're going to talk about kind of this path of how companies and technologies have evolved, and it really starts simple, right? This this is an example of simple data storage, right? This is how we did things once upon a time. But there are some problems with carving your data into stone like this. First of all, you can't really transport it. It's fixed. It's static. It's immutable, and that could be a good thing, but it's not it's not agile, right? You can't bring it to people. Everyone has to come to a single source, which you could say that's okay, but you have some critical problems with storage capacity here, right? It takes a long time to write, maybe isn't so hard to read from, but just you're so limited in what you can actually store. So people figured out, okay, well, maybe this idea of transport is useful. And also, we need something that's a little more lightweight to be able to do that. And this has some issues too, right? It actually degrades a little bit more quickly than the other method, but it's way easier to quickly produce your data in this format. Then we figured out that we could solve some of the degradation problems with replication, right? Where we're creating copies of the information, and we can do that and present the information in a compact way, which certainly helps with transport. But then, also because your data is immutable, what happens, if you produce 10,000 copies and then you realize that there was an error and you have to fix it? Well, it's not very inexpensive to fix that problem. And many of you have probably seen paper record systems. Of course, one of the biggest issues when you have information stored in this kind of mechanism is that search is not very feasible, right? What happens when you have a particular record and you have no idea where it is and you need to find it? And maybe it's time sensitive. Maybe you need to find it urgently, right? Well, you're going to have to literally check everything. Especially what happens if there's a filing error, right? And it's not where it's supposed to be. Well, then you're literally going to have to check every record. So then we figured out that there are ways that we could compute things, right? This is kind of, in parallel in this process, but we'll see how these things come together. So this is an example of Roman abacus, right, which was a simple tool used for math a long time ago, and perhaps today by enthusiasts. This is a slide rule. Some of you may have actually used one of these. I fortunately did not ever need to. And then we have the punch card reader, which is, I would say, somewhat infamous. Hopefully we all know what a punch card reader is, but truly it was revolutionary at its time. Allowed us to do some pretty spectacular things. Well, so if we look at this history, switching, after Turing invented the Turing machine, switching became automated, right? He figured out how to leverage electricity to solve computational problems. And this is huge. This spawned a huge breakthrough in the advancement of computational technology. And that was leveraged to allow storage to improve further, right? So this is an example of one of the world's first hard drives. This thing weighed over a ton. It could only store 5 megabytes, right? And this was a very expensive machine, right? Imagine how you transport this thing. But this was a revolution. You can imagine this is, once upon a time, this was a huge breakthrough. Then we got smarter. We figured out that we could compress that information. We figured out that we could leverage a lot more modern switching capabilities to be able to compact that information. And now we can store information parallel, right? And 2.5 gigabytes a second, you can do a lot with that. Right, now we also saw data transport evolve, right? So gone are the days where all the information had to be transported physically, right? On horseback or by pigeon, carrier pigeon. And you think about it, carrier pigeon at the time, that was used for critical information, right? Especially during warfare, where, you were counting people's lives on whether or not you could get that pigeon to where it needed to go. Well, then we figured out that still, there are ways that we can improve that. And some of you may remember these floppy disks. They just got a little bit smaller, but still there are problems with magnetic tape, right? It also degrades. And we figured out that we could leverage this, this idea of ones and zeros over a wire, so that people, across the country could transport information without having somebody to physically, put on their sneakers and take it somewhere. But the fact that it could be transported digitally, this is a huge revolution. And then we saw some advances in the capability there. Right? Went to 56K and then Ethernet, right? And now we're at fiber. Of course, not everybody's running fiber, but this capability has evolved and it's becoming less expensive. The data management also changed, right? I'm sure many of you have seen situations like this. Now, you notice in this case, we have a lot of paper information. It's not stored very well, but it's sort of hard to effectively store paper information. I mean, you can organize it, but you still don't solve the search problem with just the fact that you have paper. But you notice right in the center of this picture, there's a computer, right? Well, what is that computer doing? Well, maybe it was something like this, right? The guy, he's been going through all those papers and trying to collect information, and then he can put it into his computer to crunch some numbers and get some summary information that can be used to make business decisions. And now we start to see that this idea is we're taking data, we're consolidating it, and we're using it to make important decisions, right? This is a critical paradigm. But then we figured out that had some issues. We wanted to be able to make it a little more compact and be able to store formulas more easily so we could have more of them, and also make it easier to get data in and out of the system and to be able to process it more quickly. Then we figured out, well, what happens when you have many of these spreadsheets? right? And you have to link them together, and you make a change in one place and you need it updated elsewhere, right? So this was the beginning of what led to formation of the relational database, right? This idea that we could link together information basically in different spreadsheets, and then have ways of processing that. Right, so we also saw the emergence of web technology. So just as an example, this is MVC. Many of you may be aware of this model view controller pattern, but the idea is that you separate the way that you're displaying your information to the user from the way that you're processing your logic and doing your calculations and handling things like data storage and those sorts of things. So then as we saw this emergence of data, as it became increasingly available, this led to technologies like Hadoop and MapReduce, which was a huge paradigm shift for a lot of people, where you could leverage computers in parallel using commodity hardware to be able to process massive amounts of data. And again, this is about this whole batch paradigm. However, limitations were discovered. And so we'll talk about some of these examples. So for example, MVC doesn't scale well. This is what tends to happen. This is research that was done by Facebook when they were developing React, which is web technology. They figured out that you end up with, it becomes kind of a scatter plot here, this diagram where I guess this would be more like a bipartite diagram or graph. But the issue is that your models and your views, they end up with these dependencies between each other, and you make one change somewhere, and then you have this cascade of breaks, of things that it broke. And then you have to update each of those, and then it's, it can be kind of like whack-a-mole. We're trying to just get all the errors resolved, and in doing so, you end up creating more errors in the process. So something had to change. Another example has to do with what happens to we call data lakes or data warehouses. The idea is we have consolidated data storage for large volumes of data or large varieties of data, both of which present as big data problems. When we talk about big data, a lot of times there's an assumption that we're talking about exabytes or petabytes of data, but that's not necessarily true. It doesn't have to be that case. You can have smaller volumes of data, but if you have large data variety, you still have to leverage big data types of solutions to be able to solve the problems, such as data fusion. So for one case, you have valuable data, but it's scattered. Right? It looks like this. I mean, you can go through, but you're going to have to organize it better. Hopefully it doesn't require too much cleanup, but of like individual things, it seems to be fairly intact. The mess is encapsulated, but it's still going to require some work to get organized. Another case is where it's organized in a much more scattered, widespread way, and you have lots of collections, but each collection is not organized like this. In this case, you do have data that's a mess. You've got spills that are going to have to be cleaned up, and this is going to require a much more widespread effort. A lot more people are going to have to be working on this. And then the worst case is where your data is just trash, right? Where nothing is useful. And this is a problem that can occur when we don't solve data fusion problems correctly. It's probably one of the most common reasons that data can end up like this. If you don't have enough context to your data, you can end up with data that's completely useless. And it can be as simple as omitting a single field when you're capturing that data. It can be, for example, if you're collecting information about transactions, but you don't know who the transactions were associated with, and you have no idea, or if you have no actual way of being able to link a transaction to a person, well, guess what? Your data is worthless. Maybe you can recycle something, right? But in terms of supporting analytics and your business requirements, unless you have some way to be able to put some kind of context together, I mean, you can really, just by omitting a single field, you can really substantially degrade the value of your data. And then what happens when we use data like that? We look like this, right? And everybody sees it. Everyone knows it. And you can end up with reports that are inconsistent. You can end up with all sorts of problems, and everyone knows that it smells, doesn't look right, doesn't seem right, doesn't feel right. We don't want to be this guy. So a good data lake or data warehouse or streaming platform should look more like this. Okay, the idea is this is a data pantry, right? You can pick and choose what you want. Everything's labeled, everything's organized, everything's consistent. You don't have to worry about whether or not something is what it says it is. It's nice and clear and easy to use, friendly for the user, and it doesn't make you feel gross inside when you're putting things together with this. Okay, now this brings us to a critical junction, which is that the solution is not the technology. The technology is the tool. Okay, the people create the solution. Those who are using the tools can create the solution. And this is so important to understand because unfortunately in today's society, through the diligent marketing efforts of many companies, they always try and sell their technologies as the solution, right? Well, but it's sort of a lie because it's so easy to have a technology. It could be the best technology in the world, but if you use it for the wrong thing, it's not going to do what you want. Or, it could be so expensive to use that you're not really going to get the value out of it, right? And so using the right technology for the right problem, the right solution is so important, and that requires engineering. So why do data disasters occur, right? If it's so obvious as to how we can prevent some of these problems, why does it happen? Well, it can happen when we lack data governance. And these are problems that don't happen overnight. They tend to be evolutionary problems, problems that just sort of end up existing, typically when an organization is doing everything right. And this is what makes these problems so sneaky. Because they can sneak up on an organization that is following best practices and doing everything right, and then suddenly they end up with a situation like this. This is LinkedIn, and LinkedIn realized that they had a problem, right? They were doing everything right, and how they were structuring their data processes, but they realized that it was not scaling, and they said, hey, we've got a problem, we've got to fix this. So they invented Kafka. Kafka is a very influential technology that introduced this idea of a streaming pipeline. It's an immutable log that is high performance and highly available. And the idea is that you use this technology to communicate between different technologies. So the idea is that you write to a topic, and then you can have apps that subscribe to the topic. These are Kafka topics. And so you can push data, and you can have many topics that allow that data to be nice and organized in terms of how it's communicating with everything. So other technologies said, hey, we should do that too. And so Facebook invented Flux architecture, and this architecture that they made possible really draws this idea of a flow where you have an action. The dispatchers function sort of like a controller, that accesses your data store and presents something to the user. And then based on the user's interaction, and this is a key thing we want to pay attention to, that interaction then drives some action in your technology that ultimately will access data store, which could include writing information to your data store and then presenting updates back to the user. And this can happen very fast in real time. So as we noticed that this concept of real-time interaction started to emerge in terms of how we interact with our users, we started to recognize that there were really two separate paradigms. There's batch processing, and then there's stream processing. And so we have to consider them as separate things because the use cases are actually quite different. For example, you can't effectively use batch processing for real-time customer interaction, right? Because, it's like, imagine somebody trying to use Facebook if it took 24 hours every time they clicked the button to get something new, right? It's just not going to make any sense. But the underlying technologies that you have to use are very different when you're processing stream data. So what is stream processing? This can be confusing for folks. So when we talk about event streaming or stream analytics or real-time or near real-time or event-driven or reactive, okay, this is all really about the same thing. And that leads us to talking about these ideas like proactive and predictive. Okay. Now, before we get to some examples, I want to make a point here. Real-time analytics, it is a game changer. It changes everything in your business and how it changes everything about the capability that you can offer to your customers that nobody else can. And we're gonna dive into this. So let's consider an example with credit card fraud. Okay, imagine you get a phone call from your bank, and your bank says, oh, hey, by the way, I don't know if you noticed, but somebody in some other country charged up $10,000 on your account, and we realized it was a fraudulent transaction, but we're really sorry, there's nothing we can do. It happened a long time ago, and somehow you didn't notice. Shame on you, right? Okay. Now let's compare that to the case where instead you get a phone call from your bank and they say, we noticed that somebody in some other country just now tried running a transaction. Should we approve it or not? Okay, now this is what real-time analytics provides. Okay? This capability is so influential because now you can make a decision, right? It was based on historical information that they had processed and made available in real time with some kind of analytics engine, right? And then here's an example. This could be real-time customer support. In this case, this is an example of educational technology. This is from a presentation at the Learning Analytics Conference in, I believe, 2017, where there's a presentation by some folks at Carnegie Mellon who talked about this idea of using augmented reality technology to be able to see what a classroom of users were doing in real time. And you can see, in this case, which students need help, which students really need help, and who's not paying attention. And so this idea of being able to leverage analytics to be able to gain insight into your customer in real time is really extraordinary. And then financial decision support, right? Being able to get supportive information to guide transactions and whether or not they're going to be successful. And then blockchain is a really good example of a streaming technology. I mean, everything about blockchain is streaming. It's all real time. And the idea that you could have transparency in that process is really revolutionary. And so this is an example of Medici Ventures portfolio. Right now, Medici Ventures is an Overstock subsidiary. They're doing some really brilliant things. So I encourage you to check them out. So let's also consider this example. Have you ever needed to change your plans because you received critical information too late? Okay, think about it. Maybe an even better example is, what about those times where, oh, if only you could remember that thing yesterday when you needed to remember it, right? And maybe it was a holiday, with your spouse or something like that. I mean, I'm sure we've heard of some horror stories. Um, so let's think about the importance of being able to get critical information at the right time. So what do the most profitable internet companies have in common? And how does this relate? We're going to look at this pattern here. So if we look at these companies, what we notice, first of all, they're all technology companies. But secondly, they're building platforms that allow self-service for the user. They're building self-service data streams as a platform. If you think about it, without data streams, none of these technologies would exist, right? I think Google is probably the foremost example here because their product, right, started out so simple, at least in terms of what the user saw and interacted with. And it's a data stream for them because that customer data comes in real time, it's processed in real time. Now, under the covers, they had other kinds of batch technologies that had to be used. However, what we're going to talk about here is how that paradigm is becoming obsolete, where we're able to leverage stream processing for everything. And there are some substantial benefits that we gain when we use stream processing for everything instead of using the batch paradigm. But all these technologies provided self-service platforms. And what that allows you to do as a company is utilize your customer data to be able to enhance your product more. Right, based on the things that you learn from your customer, you can then figure out what their needs are and what they want from you in new and better ways. And you can offer them support and products and services that you never imagined because you can figure out exactly what they're wanting the most in real time. So what we see is that the most profitable companies are figuring out ways to allow their customers to create data flows that drive core business processes. They're no longer just focusing on data stocks or like data collections. They're looking at the data flows. And we see that the emergence of digital data streams is creating strategic opportunities for existing firms and enabling the formation of new enterprises. So Streamlio worked with a company called Dimensional Research. Streamlio is the company that supports Apache Pulsar. Pulsar is a real-time streaming technology that has been quite revolutionary. We're going to talk about it more here soon. And Dimensional Research surveyed 307 IT decision makers who are responsible for corporate data solutions. And they asked some questions and got some information. So this first question is, how important is it to your organization that you're able to process and act on data as quickly as possible. We're not going to look at all the questions that were asked, but we're going to start with some of these. And what we see is that 99% of the surveyed companies said that it is important to process and act on data as quickly as possible. Very few didn't see that as being important. And of those who say it's important, or of those, it might have been of all of them who were surveyed, how many say it's critically important? Okay, so of those that say it's critically important, we see there's a split according to the size of the company. Now, of course, if your company is bigger, you have to be faster. A lot of larger companies can struggle with being agile, and so they recognize the pains associated with poor company agility much more, because you can have some new kid on the block who spins up some new technology, who is more agile and innovative than you are, and suddenly they just sucked up some chunk of your market, and now what do? So still, even across these cases, in all these cases, we see that it is widely recognized that acting on data as quickly as possible is critically important. Now, not everybody recognizes that, but a lot of people do. This leads me to a warning here. If it takes your company more than hours to answer data questions, your company may be in serious danger. Think about it. If you can't answer questions quickly, how do you iterate on those? It takes too long, and you'll be too slow, and you'll get crushed in the industry. So for what types of applications would your organization benefit from processing data immediately rather than in batch? Okay, so if we look at these different cases, I want to focus on this central theme here, which is directly enhancing the customer experience. Now we see that customer interaction specifically is marked here, but one step above that, in security and fraud detection, well, we just looked at the banking example, right? That's an example involving security and fraud detection that affects the user in real time and affects the customer interaction. And we can see ways that all of these different categories can affect the customer directly. Reporting is another example, right? If you're using a product and you want real-time reports on what's going on inside your organization as your organization uses that product, that's another good example. So what benefits can your organization gain by processing data immediately as it arrives rather than waiting to process it periodically in batches? Okay, and again, this brings us to this focus point of directly enhancing the customer experience. Right? Now, ultimately, for streamlined operations, that means that you're able to serve your customer more effectively, right? You're able to serve them faster. But even explicitly is mentioned 60% of cases here to enable real-time customer interaction, right? And they use some specific examples like personalization, promotions, recommendations. Think about how personalization and recommendations have been so influential when we shop online, right? Or when we use the Google search engine, where we see what we're looking for based on what our data has shown our interest as being, right? For example, if I'm doing a search on Amazon for something that I want to purchase, right? I don't want to see ads related to things that I don't care about, right? I want to see ads related to, if I'm going to see ads, I want to see things that I'm actually interested in. And I certainly don't want to see things that I definitely don't want to see. Like, I don't want to see women in swimsuit bikinis. I don't want to get advertisements on coffee pots, right? Those kinds of things. So this capability really substantially improves the direct customer experience. So which of the following additional technologies or technology capabilities would your organization find valuable? And again, I'm trying to really drive this point forward. It's about directly enhancing the customer experience. So real-time analytics and the ability to query data immediately as it's received were the two top reported items here. So then how would the technology capabilities from that previous question benefit your organization? And look here, about directly enhancing the customer experience, number one reason is to increase customer satisfaction. And then just below that, enabling new data-driven applications that were impractical or impossible before. And then just below that, support expanded access to real-time data to more users. Okay, all of these are focused around how we can leverage real-time technology to gain capabilities that otherwise we did not have. Okay, so this brings us to an important junction, which is where we look at the difference in value of data over time as we see the transition from a single datum to that data in aggregate form when we're looking at larger volume. We see an exponential decay of the value of individual datum, and we see an exponential growth in the value of that data in aggregate. And if we look at the time frame, right, interactive time frame, we're talking about milliseconds. This is like, think about like the responsive web app example or social media, for example. It's real-time analytics where we're getting that summary information presented real time. That could be as simple as number of followers on your Twitter. Well, actually, maybe a better example is like number of retweets for a tweet, right? If suddenly your retweet count goes up to 100,000 over the course of 30 seconds, you know that something huge just happened, right? Especially if that historically has not been the case, right? So that's an example of real-time analytics providing important information in real time. But then, as that, even in that case, we see that there's, that capability requires more data volume, right? You had to know more things about more people and what was being done. And then, as we step further down the path of having larger volumes of data, like in the fraud case, the banking example, you have to have processed a lot of data to find that many enough fraudulent transactions to be able to understand what kinds of transactions are fraudulent or what fraudulent transactions look like in terms of patterns. So now what if we could combine these capabilities? Now, if we could combine the interactive capability with this exploratory power, it's really power, can we do that same thing with stream processing? And the answer is yes. Stream processing is key to accomplishing this. Now, I want to mention here that a full-featured solution may involve other technologies as well, such as graph technology. Graph technology can be very influential in allowing you to connect a lot of things together that otherwise you can't with a purely relational model. But stream processing is the key to gluing everything together. So this introduced us to this new paradigm called Kappa architecture. Kappa architecture, as opposed to Lambda architecture, which we showed in the slide that had the split between the batch and the stream processing, that was Lambda architecture. So this Kappa architecture is where we say, hey, we don't need the batch layer. We can do everything with stream processing. And I want to point out here that one of the advantages we get, and there are many, but one of the advantages we get with Kappa is it's substantially more cost effective. In today's society, data storage is much less expensive than computational processing. Now, this may not always have been the case. We looked at that example of the 5 megabyte hard drive that weighed over a ton. It wasn't very cost effective to store a lot of data. So we did everything that we could to try and minimize the amount of data that actually had to be stored, right? And that was, we talked about database normalization forms. A lot of that's focused around saving data storage, and we don't have to do that so much now. We can trade off, or we can leverage inexpensive storage to be able to store the most relevant information so we can access it as quickly as possible and process it as quickly as possible. So in Kappa architecture, you're taking data as it's coming in and you're preparing it for its use cases in real time. So the idea is that, well, there are many paradigms that can be evolved here, but like one pattern example, for example, is streaming enrichment, where we're taking data as it's coming in and we're combining it with other information. Some of that information could be stored in a fast caching mechanism like Apache Ignite, or maybe a more well-known example is Redis. There are various cloud offerings of these technologies as well. And or you could even perform a database lookup, relational database lookup, although you have to make sure you're mindful about latency and other possible performance issues that you could run into. And you're taking all this context and you're adding it to what you know about what's coming in the pipeline. And then you're storing this highly enriched wide stream of data. And then you can also perform aggregations. You can perform statistical calculations. You can perform transformations on your data, and you can do everything that you need to to process the data in real time. And one of the biggest advantages we get with that improvement, I'll give you an example. So let's say you have some very large tables and you need to join them together. And since databases are basically like a global state variable, if you think about it that way, you never know when something, I mean, unless you have really sophisticated change tracking enabled, which, by the way, change tracking is a streaming technology in a sense. You don't know what's changed in your data. And so every time one thing has changed somewhere in your data, you have to then rejoin all of it together. Now, most of that join operation is repeated calculation. You've already performed that join before, or most of it, except for just the one little thing that's changed. And that means that most of that computation is completely wasted, right? Whereas it makes a lot more sense to be able to perform that kind of joining in a stream in real time as that data is coming in, and then just store the current representation. And then we only have to look up the most recently stored representation. We don't have to do all this other stuff. Okay, so this is basically the process as we look at it. Right, you have some kind of data producing action, which is either from user or machine. It could be a device. We talk about IoT devices, right? Like sensors. That can be a source. Or they could be mouse clicks or things like that. It goes into this this fast, high availability stream pipeline, and then through our analytics engine, and then we can return information back to the user. But streaming isn't just for analytics. Streaming introduced us to this idea of this concept of serverless, which is a whole new computational paradigm that leverages computation on the fly in small pieces to be able to enhance real-time interaction with the user. And it's like peanut butter and jelly in your sandwich, right? It goes very well together, which is the point that I'm trying to make with that example. So we see that serverless is a capability that's emerged. It's really been the evolution, the step forward from using Docker containers. And then we see, even before that, we had some evolution in the technology that made that possible. And functions as a service. This is a capability that was made possible through this paradigm. We talk about like Amazon has Lambda functions, their Google and Azure cloud functions. That's what we're talking about here. This serverless capability where we're just paying for per millisecond of compute time, and it's highly elastic, very scalable. If you have some burst of data come through your pipeline, you can very rapidly multiply the number of nodes or of functions that you're processing and for that data in parallel, and it allows you to be very elastic, and it's really the step beyond these previous paradigms that were clunky and hard to maintain, like the monolithic architecture example. So what if we could combine all these ideas together? This leads us to the next generation streaming engine, which is Apache Pulsar. Apache Pulsar is a huge breakthrough in this capability. And it was inspired by many of these other influential technologies like Apache Kafka, Apache Storm, Apache Flink, Apache Heron, and then AWS Lambda, and Azure and Google Cloud Functions. So what does Pulsar offer? One of the features is multi-tenancy. This is really nice for organizations that want to be able to provide streaming support across the organization to many different people, to many different developers and users who want to be able to have different needs met. They have different security concerns, they have different use cases, and they want all of that supported. Then we have geo-replication. All right, now this geo-replication is one of the things that can be very tricky to get right in Kafka. You can have to build a lot of tooling around it just to make this feasible. It can be kind of painful. But with Pulsar, it's simple, it's clean, and it's available basically out of the box. It's really easy to set up a multi-cluster environment. And so when you want geo-replication for performance or to increase your availability and your uptime, that's really easy to do. And then security. Pulsar uses a hierarchical security model that is associated with its multi-tenancy. So you can have a tenant that has its own security tokens that allows very nicely encapsulated access control so that people can't access data that would be sensitive or that you wouldn't want them to access. There are nice ways of being able to control that. And then one of the best features is guaranteed delivery. Right, so you never have to worry about a message ending up like this. Pulsar has some very sophisticated but simple methods for guaranteeing delivery. I encourage you to look into that and into how they work. And then Pulsar also offers persistent stateful storage. This is similar, of the technologies that are out there, it reminds me of Flink, where you can maintain state in your computations, in your streaming computations. And this is super valuable, especially for the cases where you have record that you want to aggregate that only comes in once in a while, whereas a lot of other options out there require you to fit all your computation in a single window. But that's not always feasible, because let's say you have a transaction from a user, you want to be able to roll up different metrics for that user specifically. But let's say the user only comes in, they only provide us data once in a while, maybe once every several days or weeks or months or years, who knows. And so if we're looking at a window of what happened today or what happened in the last 3 hours, well, they're always going to be, or well, not always, but most of the time they're going to be outside that window. And so we don't have all that historical information available to us. Now, if we can leverage state, if we can remember the metrics that we calculate about that user and bring them back into our stream computation every time that user comes back into our stream, then we can roll up metrics and perform calculations based on where we left off. This is a super powerful capability, because this is the capability that allows us to start offering the things that batch technology previously became so famous for. But we're doing it extremely fast. And Pulsar specifically was designed for latencies below 5 milliseconds at scale. So think about that. Compare that to hours of latency with the batch paradigm. Pulsar also offers horizontal scaling. This is really nice because you can get parallelization out of the box to be able to process your data more effectively as you scale up. And then you have stream organization. They even have some UI interfaces that are really useful for looking at your metrics, and it allows you to, especially with the hierarchical structure, it allows you to easily keep track of different functions that are running on your different topics. It's a nice, clean organizational structure. So it's not a mess like it can end up with Kafka. If we're trying to run functions out of the box. Well, Kafka doesn't really support functions like that. You have to build it yourself, and it's a lot more work. Whereas Pulsar does support that out of the box. And so the idea is still fairly simple. You have input topics. You can have one or many input topics to a function, and your function can process to a log topic and to one or many output topics. Your function can do all sorts of computations. It can do database lookups. It can do windowing operations. It's kind of up to you to determine how you want to design that. And if we think about what data scientists spend the most of their time doing, unfortunately, it's data engineering. They should be doing data science, not data engineering. Why are they spending almost 80% of their time collecting data sets and cleaning and organizing their data? Now, some people could argue, well, it's important for our data scientists to be able to fully understand the data they're using, yada yada. But think about their capabilities and how that doesn't necessarily match up with that expectation, right? Data scientists are trained, a lot of times, math and statistics and analysis. They can figure out what's in your data, right? They don't need to have to do all this other stuff first. They can communicate those needs to a data engineer who's really good at doing things like filtering and aggregation and enrichment and doing all that in a streaming manner and presenting it in that data pantry format and saying, hey, look, here's your nice, clean, pre-processed data, right? Otherwise, it's like asking the guy at McDonald's who's making your hamburger to have to go out in the field and harvest all the wheat and then put it in a milling machine. And okay, yeah, you could say, well, it's important for them to understand that process. Yeah, but that doesn't mean they should have to do it every time, right? It's like, well, it's important for them to understand the different characteristics of the wheat that they're processing. Well, is it really? Couldn't somebody just tell them that? And somebody who's better at processing that actually might be able to get more information about what's actually going on because they're familiar with that process. Right? So we shouldn't be having our data scientists be spending only 20% of their time doing data science. That just is silly. And interestingly enough, The fact that so many data scientists spend so much of their time doing data engineering shows that we have a huge deficit in the industry for data engineering. Clearly we have a need here for data engineering. There's a disproportionate demand for the market supply. That means that this is a very valuable area for you to focus your career around, because there's a huge need. And this need has largely started because organizations, they've wanted to obtain the benefits of machine learning and AI and predictive analytics because they've recognized the value that can provide, and they want to be able to leverage data science to be able to do that. But they didn't know that their data was a mess, or they didn't know how to effectively solve these kinds of problems or make this data nice for data science. A lot of organizations just sort of evolved into this situation. As the industry evolved, they tried to catch up, and the problems just sort of came to be. Data engineering is what solves that problem. It's what opens doors for machine learning and analytics. So real-time processing of streaming big data is crucial to finding meaningful data and reacting to it. And pre-processing can improve performance by many orders of magnitude. Ultimately, good data leads you to great machine learning ROI. And the lesson learned here is you should drive with your market, not your cost optimization. Okay? So if you want to spearhead machine learning or analytics or data engineering efforts, you've got to tie them to initiatives, company initiatives that are designed to generate revenue, especially if it's about enhancing a core capability with your user. You never want to take the other approach and try and spearhead it from optimizing your costs. So streaming and machine learning applications will be significantly more successful if they directly enhance the customer experience. I've said this multiple times and I keep stressing it, and I hope that if there's one thing that you can remember from this presentation, this is one of those. And then Overstock is hiring. Please, again, reach out to me or our recruiter, Paul Kerr, if you have any questions. We are doing some fantastic things. We are leveraging Apache Pulsar. We're working very closely with the folks at Streamlio, and we are building high visibility real-time pipelines that directly support machine learning as revenue generating initiatives. And we are doing some really cool things. And thank you for watching this. My slide deck is also available on SlideShare, and I hope you have a wonderful day. All right, thank you so much. And please feel free to give me any feedback. I would love to know how I can improve this presentation or how I can help answer questions. All right, thanks.